Without an operating system, a motherboard remains a static assembly of inert plastic, precision-milled metal, and cold silicon. It lacks the logic required to calculate, display an image, or facilitate a network connection. The central processing unit is the physical brain of this computer architecture, but while it can execute billions of instructions per second, it is functionally blind without a software layer to feed it specific commands. This foundational layer is the operating system. It is defined as system software, a complex collection of programs designed to manage hardware resources while shielding the user and application programs from the raw complexity of the machine. The OS serves as the interface bridge between the user and the computer hardware. When you launch a browser or save a file, the OS interprets that high-level request and translates it into specific signals for the physical components. To understand how this architecture functions at an exam level, we categorize the OS into three primary pillars: process management, memory management, and information management. These three pillars work in tandem to ensure the CPU, the RAM, and the storage drives interact without conflict, allowing you to run multiple high-demand programs simultaneously. We begin with process management. In this context, a process is a specific task that has been loaded into the RAM and is currently under execution. Every process cycles through a specific lifecycle. The operating system tracks these tasks through three states, starting with the running state. A process enters the running state when the CPU is actively reading its code and performing calculations. If a task requires an external event to continue, such as user input or the completion of an I/O operation, the OS moves it into the blocked or waiting state to free up the processor. Once the necessary event occurs, the task moves to the ready state. It is fully loaded in memory, waiting in a queue for the OS to assign it its next slice of CPU time. This rapid movement between states is what allows for multitasking, facilitated by a core OS function called context switching. Because a single core CPU executes only one process at a time, the OS must rapidly save the state of one task, pause it, and load the next. This cycle repeats thousands of times per second. The microsecond required to perform this switch, where the CPU is performing no productive work for the user, is defined as idle time. Multitasking is effectively a high-speed illusion. The OS switches context so frequently that the human user perceives multiple applications as running at the exact same time. For these processes to exist, the OS must allocate them a physical location in the RAM. This is the second pillar, memory management. Early systems utilized fixed partitioning. The RAM was divided into rigid, permanent blocks of specific sizes, such as a 4K or 12K segment. If the OS assigned a 3K process to a 4K block, it fit, but could not utilize the entire partition. That leftover 1 kilobyte of space becomes inaccessible to any other process. This specific type of memory waste is known as internal fragmentation. As the number of active tasks increases, internal fragmentation limits the total number of programs the system can hold simultaneously. Modern systems utilize variable partitioning to bypass this limitation. In this model, the OS creates partitions that dynamically match the exact size of the incoming process. By snapping the partition boundaries to the data, variable partitioning removes internal fragmentation, maximizing the system's capacity for multiprogramming. The third pillar, information management, handles data before it reaches the RAM. It manages how files are stored and retrieved from permanent physical media. Early computers relied on magnetic tape reels. Retrieval was strictly sequential. To find a file, the drive had to physically spool through the entire tape until the correct data passed under the read head. Modern hard disk drives utilize a more direct retrieval method. The platter surface is divided into concentric circles called tracks. Each track is subdivided into pie-shaped slices. The intersection where a slice meets a track is a sector, the smallest unit of storage. When the OS requests a file, a mechanical arm moves to the correct circle. The time required for the head to reach the specific track is the seek time. The subsequent period spent waiting for the disk to rotate the required sector under the head is defined as latency time. Because seek and latency times are bound by physical movement, the OS employs different allocation methods to organize how files occupy these sectors. Contiguous allocation stores a file across sequential sectors. This results in fast read speeds, but makes finding a single large gap for new files difficult as the drive fills. Linked allocation allows the OS to use scattered sectors. Each block contains a pointer to the physical location of the next block in the sequence, making better use of available space. Indexed allocation is the most refined method. It designates one central block as an index that contains the addresses of all other scattered pieces of the file, allowing for more direct access. By moving from contiguous physical sequences to indexed data networks, operating systems minimized the mechanical travel of the drive head, accelerating overall data retrieval. We can trace the evolution of these architectural pillars by looking at how the user interface has changed over time. In the early 1980s, MS-DOS operated as a single-user, single-tasking system. Users interacted with a text-only interface, requiring the memorization of specific commands to perform even basic file operations. The shift toward the graphical user interface, or GUI, replaced text commands with visual icons. Popularized by systems like the Macintosh, this interface made computer operation more accessible through a mouse and visual metaphors. With the release of Windows 98 and Windows NT, multitasking and GUI-based management became the standard for mainstream personal computing. At the same time, Linux emerged as an open-source alternative. Its kernel optimized multi-user functionality, running reliably on various hardware architectures. The transition from typing manual commands to clicking through icons was enabled entirely by the advancements in memory and process management we have explored. As OS architectures moved from isolated computers to connected networks, security protocols shifted from physical locks to software-based logic. Modern operating systems are designed around a foundational security policy known as the CIA Triad. Confidentiality ensures that data is readable only by authorized individuals or processes, using the OS to control all read operations. Integrity focuses on preventing unauthorized modification. The OS monitors write operations to ensure that information is not deleted or altered by unapproved users. Availability ensures that the system and its data are reliably accessible to authorized users when needed, managing resources to prevent system-wide denials of service. Understanding these core mechanics of process states, memory allocation, and the CIA Triad provides the technical framework necessary for both system design and board examinations. For more detailed reviews of computer science fundamentals, subscribe to the channel.